All right, so this is the single value decomposition for linear transformations from last time. So just to remind you, you have a linear transformation from a space V of dimension n to a space W of dimension m. Then there exist orthonormal bases, one for V, one for W, and there exist strictly positive scalars arranged in decreasing order, sigma 1 greater than sigma 2 greater than sigma r, with the property that T of Vi is sigma I ui between 1 and r, where the sigmas are defined. And they are uniquely determined by T, and they are found by looking at T star T. VI's are the eigenvectors of T star T, and the squares of sigmas are the eigenvalues of T star T. Telling you last time that we're going to do one more example. This is 2b in that section. The linear operator is T from P sub 2 of R to P sub 1 of R. That takes the second derivative. P sub 2 and P sub 1 are inner product spaces, both of them with the following inner product. The integral from negative 1 to 1 f of t times g of t dt. And you have to find the singular values and the two bases for the orthonormal basis from the theorem for P sub 2 and P sub 1. All right. So the theorem is calling for this operator here, right? T star T. Remember that it's not always easy to find the adjoint, of an operator as a formula, as a function, but it's simpler to look at the matrix associated to that. It has to be the matrix in an orthonormal basis, though, because only with orthonormal basis you can pull out the star from inside and move it outside. So we have to start with T star T again. So T is defined on P sub 2 of R. It takes you into P sub 1, and then T star goes from P1 to P2. So T star T is defined on P sub 2 with values in P sub 2. That has dimension 3, right? So we're looking for a 3 by 3 matrix. But it has to be the matrix in an orthonormal basis, right? So we need an orthonormal basis for P sub 2. We can start with a standard ordered basis for P sub 2, which is 1xx squared. At which point you can apply Gram-Schmidt, right, to make it orthogonal, and then normalize each vector, and it turns into an orthonormal basis. Which for P sub 2 will be the following. Square root of 5 over 8 times 3x squared minus 1 is the last one. Let's call this basis beta. So this is an orthonormal basis for P sub 2. I'm skipping this step. Again, on the exam, you will be given directly the orthonormal basis. All right, so now I want to find the matrix of T star T in this basis, which is the matrix of T star times the matrix of T. I cannot say both in the basis beta because T goes from P2 to P1, so the matrix of T will be from beta to beta prime, where beta prime is an orthonormal basis for P sub 1. And this is from beta prime to beta. However, you don't have to compute both because, again, being orthonormal, the star can be moved out. So you only need to find the matrix of T and then multiply it by its adjoint. And so this was beta. Who is beta prime? Well, to find an orthonormal basis for P sub 1, you start again with a standard basis for P sub 1, which is 1 and x, right? And you make that orthogonal to Gram-Schmidt and divide by each vector by its norm to make it orthonormal, and you're going to end up with this. And the first two vectors from beta will form beta prime for P1. Okay, so let's see. So T goes from P2 to P1, so it's a 2 by 3 matrix, right? It goes from dimension 3 into dimension 2, so the matrix is 2 by 3. And the first column of this matrix is given by T of the first vector of beta, expressed in terms of the vectors of beta prime, right? So if you apply T to the vector 1 over the square root of 2, what do you get? T is this one over here. Oh, it's the second derivative, right? So you just get 0. So the first column is 0, 0. T of the second vector in beta, and derivative is still 0. And the third vector, first derivative is 6 times that square root times x, right? So when you take the derivative again, it's 6 times the square root of 5 over 8. And this has to be expressed now in terms of this beta prime here. So what is it going to be? 3 square root of 5 over the square root of 2 will this be after simplifications. And it needs to be written as a multiple of the first vector in, not in beta, sorry, in beta prime. Right, I have to write it in terms of the vectors of beta prime. So it's going to be 3 times the square root of 5 times the first vector of beta prime, which is 1 over the square root of 2. So in conclusion, written in that basis, you get 3 square root of 5 and 0 for the second vector. Let's call this A. And the adjoint will be a 3 by 2 matrix. This one here. So the matrix of T star T will be A star A. Again, we're expecting a 3 by 3 matrix. And this will be that matrix. All right, so now what do we do with this? Back to the theorem. So we found the matrix for T star T. So remember that T star T will always be diagonalizable. So it's going to have a basis, the space will have a basis consisting of eigenvectors for T star T. So we need to find its eigenvalues and the corresponding eigenvectors, so the basis of eigenvectors, that will form your basis for the first space V. Okay. So the eigenvectors are easy to find. Sorry, the eigenvalues. There are two of them. 45 and 0 with multiplicity 2. It's a diagonal matrix, right? So you just read them from the diagonal. So that tells you the first singular value of t is just the square root of lambda 1, which is 45. And it is the first and only singular value of t, right? Because to find the singular values, you just take the square roots of the positive eigenvalues. This is the only positive one, so this is it. You're done with the singular values. All right, so now to find the basis for the first space, orthonormal. Basis for the first space V, which is P sub 2 of R. You need to find that orthonormal basis of eigenvectors, right, for T star T. How do you find them? Well, you take lambda 1, which is 45, and compute the null space of T star T minus lambda 1 identity, right, and find the basis for that. And you're going to get in matrix form, you're going to get the vector 0, 0, 1. What does that mean in vector form? 0, 0, 1 in P sub 2 of R actually means this vector here, right? Because it's 0 times the first one in the basis plus 0 times the second plus 1 times the last. So V1 is square root of 5 over 8 times 3x squared minus 1. To find V2 and V3, you go to this space, so compute the null space of T star T minus 0 identity. It will necessarily give you two vectors, right, because it's diagonalizable, so the dimension is the same as the multiplicity. And you'll get 1, 0, 0 and 0, 1, 0 in matrix vector form. So that means the vectors will just be the ones from above. So V1, V2, V3 from the theorem are just the vectors from the, from the standard orthonormal basis, if you want, of P sub 2. All right, now how do we find the basis for the other space? Because we need to find those vectors U, right, for P sub 1 of R. Well, they are related to V through this. But we only have one singular value that we can use, sigma 1. So in that way, we can only find U1. So T of V1 is sigma 1 U1. So based on this, we're going to find U1. This is V1 here. So T was the operator that takes the second derivative, so we're going to end up with 6 times the square root of 5 over 8. Sigma 1, we said, is the square root of 45. So U1 will be this, which is what? This is 3 square root of 5, so 2, I think it's 1 of the square root of 2 after you simplify. Okay. So using the singular values, we only get this vector. So what would be a second one, right? Because we need a basis. We need two vectors in there. We need to add another one to this to form a basis. Just the simplest one possible. Put this one in. We already know that they form an orthonormal basis. Okay.
Didn't we already form these bases or anything at the beginning?
It happened that they were the same as the ones that we originally took to find the matrix. But in general, when you have an operator, things can change. So it's not like you found one, the standard one, and you run with that. No, it's not.
So if we're doing a test, you would have given us those first two, right?
On a test, those two things would be given. So you're given an operator from a space to another, and you will be given orthonormal basis for the standard ones, let's say, for both spaces. But that doesn't mean they will be the ones that you get from the singular value decomposition theorem. So we'll see another example later on today related to matrices, the singular value decomposition for matrices. There are other 2 or 3 more examples that I want to do. One of them is to understand a little bit what those singular values mean geometrically. So what are those numbers? And the idea is that those numbers actually determine how the transformation changes the unit circle. So if you have a transformation, define a linear transformation on R2, you have the unit circle there, right? The vectors of length 1. If you apply the linear transformation to the unit circle, it will turn it into something, right? What is that something? Well, it turns out that sigma, the singular values determine the shape. It's going to be an ellipse determined by the singular values of that linear transformation. So here is the idea. So let's say you have t from R2 to R2. I want it to be an invertible linear transformation. If it is invertible, then it's going to have rank 2. So it's going to have exactly 2 singular values. So I want them both to exist. So it's diagonalizable and so on. So V1, V2, let's say, orthonormal basis for R2. So I'm applying the SVD now, the singular value decomposition. So I get 2 bases, V1, V2, and U1, U2, orthonormal basis for the other space, which is still R2. And the 2 singular values of T, sigma 1 and sigma 2. Okay, so I want to know how the unit circle will be affected by all this. So here is the idea. If you have a vector in R2, in the first copy of R2, using this orthonormal basis, then that turns into A1, V has to be written as A1, V1 plus A2, V2, right? It's just a linear, any vector can be written as a linear combination like that. So when you apply T to this, T is linear, right? So it distributes nicely there. So you get A1, T of V1 plus A2, T of V2. But through the singular value decomposition theorem, T of V1 is sigma 1 U1, and T of V2 is sigma 2 U2. Right. So you imagine V1 and V2, right, being the 2 vectors that determine the first space, and U1 and U2 being kind of the axis. They are orthogonal to each other, right? So they determine the axis of the second space. All right, so let's call this first number x1, this second number x2. So the idea was that I'm interested in those vectors on the unit circle. So let's say V just sits on the unit circle. if it is on the unit circle, then its norm is 1. The inner product between V and itself is 1. Now when you expand this inner product, remember that V1 and V2 are orthogonal, right? So that inner product will become 0 between V1 and V2. So all you'll be left with is this. But the basis is more than orthogonal, it's orthonormal, so those lengths are also 1. So as expected, right, being on the unit circle means that the coefficients will have this property here. So this equals 1. All right, but for our x1 and x2, right, that means, so a1 is x1 over sigma 1, and a2 is x2 over sigma 2. Right, this was x1 and that was x2. a1 squared plus a2 squared is 1. Right, I'm looking at the coefficients of T of V, which are x1 and x2 in that new basis, u1, u2, and I want to see what x1 and x2, what property they satisfy. And it turns out that x1 squared over sigma 1 squared plus x2 squared over sigma 2 squared has to be 1, and this is just the equation of an ellipse. When x2 is 0, x1 has to be sigma 1, right? When x1 is 0, x2 has to be sigma 2. So that's exactly what I was saying, is the singular values determine the transformation of the unit circle somehow through the operator, if you want to see that geometrically. Two more ideas. For certain operators, it's much easier to find the singular values than for others. What operators? The normal and especially the self-adjoint ones. So if an operator T is normal, and it has eigenvalues lambda 1 to lambda n, and the singular values of T are just the absolute values of the eigenvalues. Like that. So how do we find the singular values of T? We look at T star T, right? The eigenvalues of T star T. So T star T. Well, let's just start with an eigenvalue of T. T of lambda I. T of xi. So let's say x is an eigenvector corresponding to some eigenvalue lambda I. Being normal, remember that tells us something about how T star behaves with respect to this eigenvector. It will be an eigenvector for T star as well, but the corresponding eigenvalue will be the complex conjugate. So this is lambda I conjugate times x. So then if I go to T star T, I get T star of lambda ix, which is T star is linear, right? So lambda I is being a number, can be pulled out. So lambda I times T star of x. But T star of x is lambda I complex conjugate times x. So here it is, T star T applied to a non-zero vector equals lambda I absolute value of lambda I squared times x. Therefore, the eigenvalues of T star T are the squares of the absolute values of the original ones. So to get the singular values of T, we're supposed to take the square root of the eigenvalues of T star T. So I'm just taking the square roots on top of that, so I just get the absolute values of the original eigenvalues for T. Okay. So pretty simple. You don't actually have to go through T star T in order to find those. It's even simpler if T is self-adjoint. Because if it is self-adjoint, then in particular it is normal. So its singular values will be the absolute values. According to the example above. However, being self-adjoint also implies, as we've seen last time, I think, that all the eigenvalues are positive real numbers. So there is no need to take the absolute values above, right? So you just get back the original eigenvalues. So in conclusion, the singular values of T are just the eigenvalues of T. Now, why? This is the connection between eigenvalues and singular values. But why would people bother to compute singular values if they had eigenvalues? Well, if you have an operator T, the eigenvalues, remember, they could be complex numbers, and most of the times they will be complex numbers. The singular values, though, are not, right? Singular values are necessarily real. That's how they are defined, and that's why it's much simpler to work with them. And that's why you decide to go through this whole process to get those singular values. Okay. So the same thing can be defined for matrices. The singular value of a matrix, n by matrix A, are the singular values of the linear transformation L sub A. Remember what L sub A was? L sub A of a vector is just left multiplication by A of that vector. So the vectors, if A is m by n, the vector that you multiply A by has to be n by 1, right? And after multiplication, the result will be m by 1. So this left multiplication transformation goes from Fn to Fm. But anyways, it is a linear transformation, so you can apply the singular value decomposition, the previous theorem, to L sub A. So when you apply the previous theorem to L sub A, you're going to get a set of singular values for L sub A, which by definition now they are the singular values of the matrix A. And also that theorem gave you those bases, right? They gave you a basis for the first space, which is Fn now, and the basis for the second space, which is Fm now, right? But this theorem here doesn't really talk much about those, but they will be used to come up with two matrices, U and V. A matrix sigma, what is sigma? Sigma is just a diagonal matrix with singular values placed on the diagonal. And you have this very, very useful, I would say, a nice decomposition for the matrix. So U sigma V star. Those matrices, U and V, are not any kind of matrices. They are supposed to be unitary. Unitary for a matrix means the same as it meant for a linear transformation. That is not called A, it's called U. It was normal plus something else, right? Yes. And for V, it means V star equals V star V equals identity n by n. So we'll take a look at the proof to see how to construct those matrices. But since I have this link here, let's just look at one more application. So I was telling you that one of the main applications of the singular values are in image processing and data compression. What is explained here is that any image, first of all, can be represented as a matrix. How? Every pixel, right? If it's a black and white image like this one, then every pixel has a certain number attached to it on the grayscale, right? Between 0 and 1, white and black. You attach one value to each pixel. And then if you have a certain number of pixels, like this image here is, oh, I can't write on that, of course. So this image here is 298 by 298 pixels. So that means you can attach to this image a 298 by 298 matrix. Okay. If the image would be in colors, you see above the picture there that you can represent the pixels according to their red, green, and blue. It's a bit more complicated. You get a larger matrix, but still doable, right? So now, if you just concentrate on a grayscale image like this one. So again, 298 by 298, it's a matrix, and for that matrix, you can, of course, compute the singular value decomposition, right? So you can find the singular values of that matrix. Now, this matrix will have 298 singular values, right? A lot of singular values. However, and imagine them being arranged in decreasing order, right? From the largest to the smallest. Here's what happens. So this was the first one where it says true is the original picture. K equals 10 means you just keep your first 10 singular values out of 298 and kind of reduce the matrix there. Construct a matrix with only those 10 singular values. This is what you get. Pretty bad, right? But still not that bad. Look at K equals 20. Much better. 20 out of 298. K equals 50. 50 out of 298 is still a big difference, right? And the image is almost the same as the original one. And by almost, I mean this guy goes ahead and computes. It turns out that it contains pretty much 99% of the original picture, right? So that's what I was telling you for storage purposes in general. The singular values are the best tools to work with matrices. Okay. Let's go back here. So who are those two matrices, U and V, and how do you find them? So we have this linear operator, left multiplication by A. So from Fn to Fm, being a linear operator, you can apply the singular value decomposition theorem from last time. to this operator L sub A and get a set of singular values. You get an orthonormal basis for the first space Fn, V1, V2, Vn, as it has dimension n. You get an orthonormal basis for the second space, which is Fm, which we call U1, U2, Um. And there is also a connection how to go from V to U. The operator, which is called LA, of VI equals sigma I UI, right? That was the connection between them, but only for the first R vectors where sigmas exist. Everywhere else, there is no specific connection between them. All right, so all this structure, we already have that, right? It comes from the previous theorem for operators. What does this theorem want? Well, we need singular values, we have them. We put them into a matrix, m by n matrix. We can do that, right? You just place them on the diagonal. There will be r of them, and then everything else will be 0 until you get to this size, m by n, what sigma should be. Okay, so the only thing is about those two matrices, U and V, and checking that relation over there. And they are going to be defined in the simplest way possible, starting from this data that we have. Find the matrix U, you're just going to place the U vectors next to each other as column vectors, right? You just attach them next to each other until you get a matrix. There are m vectors, each m by 1, so that will turn into an m by m matrix, right? This is exactly what we wanted for U. Do the same for V by stacking the V vectors next to each other. Each of them is an n by 1 vector, so overall this will become an n by n matrix. So let's just check. I mean, they cannot be any kind of matrices. They have to be unitary, right? So U star U equals U. So let's just check for one of them, and then I'm going to check this. So let's look at U star U. It should be the identity m by m. It's a product of two matrices. I want to find the ij entry, and I want that to be the Kronecker symbol, right? Delta ij, in order to give me the identity matrix. Now, if U is this, what is U star? Well, the first column, which is U1, by taking the adjoint, which is transpose conjugate, will turn the first column into the first row, but with complex conjugates, right? So I can just say U1 star and imagine it going as a row instead. The second row will be formed by taking the second column, right? Take the transpose, it becomes U2. Transpose conjugate, it becomes U2 star. And so on up to, down to UM star. So now imagine multiplying those two matrices, U star and U. I'll just place them in the order in which I would multiply them. All right, so U star times U. I would take the first row of U star and multiply it entry by the first column, right? That's how you multiply matrices. First row of the first matrix times the first column, entry by entry. That would give me the 1-1 entry of the product, right? To get the 1-2 entry, I do the first row times the second column. To get the ij entry, I do ith row times the jth column. But again, multiply them entry by entry. The jth column is uj in the second matrix. The ith row is ui star. But if I write it like this, what does it mean with a standard inner product? I take the sum of each entry of this times the complex conjugate of that. Does it still make sense or not much? So I'm saying that this is the same, this way of writing it is the same as this product. One row times a column, but again, how do you multiply the first entry by the first plus second entry of the row times the second entry of the column and so on? It's exactly like the standard inner product is behaving. And that would, of course, be the Kronecker symbol because the basis was orthonormal to start. All right, so this would be the reason behind why U and V are unitary matrices. So finally, let's take a look into this. So why is it the case that A is U sigma V star? Well, remember that V star V is the identity. So if I multiply this equation by V to the right, again, since V sigma V is 1 identity, it's equivalent to showing that A times V equals U times sigma. Same thing. And I'm going to do the same as above, pretty much. So I'm looking at A sub A times V, and I'm actually looking at the J column. Jth column of A times V is A times Vj. So left multiplication by A of Vj. But remember how they are connected. Left multiplication by A of Vj is in fact sigma j uj. Do the same for U sigma. Well, sigma j, the jth column of sigma, right, is just 0, 0, 0, sigma j, 0, 0, and so on. So maybe I should write it as it is. And this will turn again into uj times sigma j. So uj being the jth column of u, right? And so this is just matrix manipulation. If I'm doing here, I'm going rather quickly over that. So if you feel like it's not very clear, you can just go ahead and start writing those matrices out because there is no other way around it. And make sure it's clear how to manipulate them like this, but there is nothing more than that. All right, so let's look at an example of finding the SVD for a matrix. And finding the SVD for a matrix means two things. One, finding the singular values, but two, also finding those matrices U sigma and V such that A is U sigma V star. So it means finding the entire setting here. Okay. So I need to look at, I need to find the singular values of A, right? The singular values of A are the singular values of the left multiplication by A. In an orthonormal basis, they have the same, I mean, the matrix of LA is this matrix A here. So they are one and the same if you want. So if I want to look at T star T, I'm going to look at A star A. So going directly to matrices is like skipping that additional step for linear transformations and finding the associated matrices. So in one way, it's simpler, the first part. So if I look at A star A, I just take the adjoint. Multiplied by A. So I get a 2 by 3 times a 3 by 2, so it should give me a 2 by 2 matrix, which is 3, 3, 3, 3. A star. So I want to find the eigenvalues of A star A. So I need to look at the characteristic polynomial of that matrix. So the determinant of 3 minus t, 3, 3, 3 minus t. Which is this, t times 6 minus t. So it has two eigenvalues, 6 and 0. Therefore, the matrix A has a singular value, the square root of 6. Right, you just take the positive one and take the square root of that. So what's the matrix sigma from the theorem? What size should it have? Sigma should be m by n, same size as the original matrix, and you should just have the singular values on the diagonal. So A was a 2 by 3, so sigma, 3 by 2, so sigma is a 3 by 2. So you start with the singular values. Theoretically, you would continue on the diagonal, but there is nothing else to put there, right? So you just build out of this a matrix that has the same size as A. So that is your matrix sigma.
Would it be possible for there to be another singular value with no?
You would put it right here.
So you can't have 3.
Well, how can you have 3? Because A star A was a 2 by 2 matrix. So the max is 2. Yeah. Right, so you just continue placing them on the diagonal and then put zeros everywhere else until the size that you need to get there. Okay, to build a matrices U and V, you need those two bases, right, from the singular value decomposition theorem. So the first basis, the V's, you get them from those eigenvalues, right, and the corresponding eigenvectors. So you start with lambda 1 equals 6. And then you find the null space of the matrix A star A minus 6 identity. Is what? Negative 3, 3, 3, negative 3. If you subtract 6 off the main diagonal. And you'll get the vector 1, 1, but you normalize it, because remember, you need to make it into an orthonormal basis. So 1 over the square root of 2 times that. The other one, just subtract 0, so nothing. And you're going to get another one. 1, negative 1, which will again normalize. All right, so A star A was 3 by 2, so L sub A is going from F2, which I think is R here, it's just safe to say R2, R3. So the first basis, V1, the first basis that you get, the V's, will be a basis for R2, so you need 2 of them, right? Here they are, V1 and V2. orthonormal basis for R2. And they will form the V matrix. You just place them next to each other, you'll get a 2 by 2 matrix. So the first vector is 1 over the square root of 2, 1 over the square root of 2. That's V1. The second vector is 1 over the square root of 2, negative 1 over the square root of 2. You put them next to each other, and that will give you the matrix V. Now, to get the matrix U, we need to find those U1, U2, and so on that will form an orthonormal basis for the second space, and the second space is R3, so we need 3 of them, right? They are connected to the V's through the sigmas, but we only have one sigma. So L sub A of V1 is sigma 1 U1, so this will help us find at least the first vector in there. So you need to take the matrix A, which was 1, 1, negative 1, 1, 1, negative 1, and multiply it by V1, which is 1, 1, and 1 over the square root of 2, which I'll just move in front. So it turns into this. However, the norm of that vector is what? Is 6. So I'm going to, well, first of all, like I have to divide by the square root of 6 anyways, because this is square root of 6 times U1. So U1 is 1 over the square root of 6 times that. Square root of 2 will cancel, and that will leave you with 1 over the square root of 3 times 1, 1, negative 1. Right? That would be the first vector in the basis for R3.
How do you want to
Square root of 6 times U1 equals AV1, which is this. So U1 is 1 over the square root of 6 times this vector. Square root of 6 is the square root of 3 times the square root of 3, so square root of 2 cancels. Okay, but that's it. We only have 1, and we need 3, right? You're on your own. Come up with a second one now, orthogonal to U1. What's the simplest one that you can think of?
Yeah.
0, 1, 0 will not be orthonormal. 0, 1, 1 will be.
We start by one of those.
1, negative 1, 0.
1, negative 1, 0 also works. But forget about the square root of 3. Think about the inner product. If the inner product is 0, it will be with or without that square root of 3 in front, right? So 1, negative 1, 0 also works. If you want, I'll throw that in. But it has norm square root of 2, so I'll have to make it a unit vector. All right, need a third one. Cross product, remember? Once you have 2 of them, you come up with a third. And I'll normalize it at the end. I'll just forget about all those square roots. So I'll just look at the determinant of this matrix here, and then at the end I'll normalize it. This norm is what? 4 plus 4. 4 plus 1, 9, so it's 3.
So will we ever have to do it if something that's going in 3 dimensions, or?
Well, theoretically, yes, but on a test, no.
So how could you do it then without it? Would it be cross product with 4 domains?
No, that's the thing. It's theoretically it's getting it's more guesswork involved, let's say. But that's the extent to which it will go.
So you put it in black. The equation is in black.
Is it? Yes, you're right. So -1. This is 0. If you cross this one out, it's 0 minus -1, so it's +1. Okay, so then it's -1 here. So it's 4 plus 2, 6. So square root of 6, the norm. Okay, so now the matrix U, which is a 3 by 3 matrix, will be obtained by putting all this together. So U1 was 1 over the square root of 3, 1 over the square root of 3, -1 over the square root of 3. U2 is 1 over the square root of 2, -1 over the square root of 2, 0. -1 over the square root of 6, -1 over the square root of 6, -2 over the square root of 6. And with all those matrices defined, nobody will want to check, but this is what will happen. If you compute the product between those 3 matrices that we define, U sigma and V star, then you'll get back the matrix A. Again, why do I need that? Very, very useful in computations to be able to split a matrix into a product like that. Unitary matrices are the best because, you know, their product, you start, they're invertible, right? And very, very nice to deal with, especially within norms of matrices and stuff like that. Okay, so this is the end of the SVD. Let's just start taking a look into the Jordan canonical form. This will be a pretty long section. I'm going to start everything by looking at an example and kind of building the entire thing, the entire theory here. So let's say you have a linear operator on C7. And beta is an ordered basis for C7. Such that the matrix of your operator in the basis beta looks like this. It's going to be a 7 by 7 matrix, right? This thing here is supposed to be the diagonal of the 7 by 7 matrix. And the way in which the matrix looks is pretty much it has several blocks, right? I'm going to call those blocks. They are placed along the diagonal. The matrix is, the operator doesn't necessarily, so in general, remember, we've seen diagonalizable operators, right? Those are the best because in a basis, their matrix turns into diagonal, but we know that not all operators are diagonalizable, right? It's pretty hard for them to be diagonalizable. However, we'll see that every operator whose characteristic polynomial splits, as we still have that condition, will have a matrix like this attached to them in some basis beta. So So this will be called the Jordan canonical form of T. And beta will be called Jordan canonical basis for C7. And each of those blocks will be called Jordan blocks. Okay. So what we'll learn here is how to actually find such a thing, right? But before we go into the theory, I want to show you what kind of properties those blocks will have and what they tell you about the operator, in fact. Well, if the matrix of T in some basis beta looks like that, like the one above, we still know what the characteristic polynomial of T is. Because the characteristic polynomial of T is the determinant of the matrix of T in any basis you want, right? Minus T identity. So including this one, but this matrix, if you look at it carefully, it's actually an upper triangular matrix, right? So when I subtract T from the main diagonal, its determinant is very nice and easy. It's just going to be 3 minus T squared times 4 minus T times 2 minus T cubed, and the last one is 0 minus T, so negative T, right? However, the characteristic polynomial of an operator is not enough to help you find the Jordan canonical form, so it doesn't define the Jordan form uniquely. So two operators, T and U, with the same characteristic polynomial can have different Jordan canonical forms. Why is that? Well, imagine there exists build some operator U that in the same basis will look like this. Zeros everywhere, right? I can do that, and it has the same characteristic polynomial as T, but definitely the Jordan blocks are not the same. Yeah.
Every Jordan blocks would be a triangle.
Yes, so a Jordan block by definition needs to have the same number on the diagonal. You see, like if you look at 3, 3, 2, 2, 2, so the main diagonal must contain the same number, and then on top of that, you're only allowed to have 1 on top of every number of the main from the main diagonal, and then zeros. Okay. But it's also allowed to be a 1 by 1 block, right? So that's why this last example here qualifies as, a bunch of Jordan blocks, but they are different from the ones above. All right. So now let's talk a little bit about the vectors in the basis beta. Let's look at V1. What will T of V1 be? Well, to find T of V1 helps you find the first column, right, of the matrix in the basis beta. So T of V1 is just 3 times V1, because the rest of the coefficients are 0. And V1 is a vector in a basis, is non-zero, right? So it's an eigenvector for T, and this 3 is an eigenvalue. Okay, so V1 is an eigenvector, but can you say the same about V2? What happens with T of V2? Well, T of V2 is in fact V1 plus 3V2. It's not an eigenvector anymore, right? However, there are others in the basis beta that will be eigenvectors. Which ones will they be? The fourth one is an eigenvector, correct? Because T of V4 is 2V4. Any other one? What about V3? The single block. The one-dimensional block. What does that tell you? What is T of V3? 0v1 plus 0v2 plus 4v3 plus 0, 0, 0, 0, right? So T of v3 is 4v3, so v3 is also an eigenvector. So v3 is an eigenvector, v4 is an eigenvector, and there is one more. It's not 2, it's not 5, it's not 6, it's going to be 7. T of v7 is what? 0, but that's 0 times v7. It's an eigenvector corresponding to the eigenvalue 0. This is the characteristic polynomial, right? So I know that the eigenvalues, I know what the eigenvalues are, right? The eigenvalues will be 0, 2, 3, and 4. Because those are the zeros of the characteristic polynomial of T. And they are placed on the diagonal there, right? Scroll down. So we said T of V3 was 4V3. So V3 eigenvector corresponding to the eigenvalue 4. V3, V4, T of V4 is 2V4. That will correspond to 2. And V7. So V1, V3, V4, V7. Among this will be eigenvectors. What about the rest? What are the missing ones? V2, let's take the first one. T of V2. They will not be eigenvectors, but let's see what happens with those. Because they still have some nice properties, right? Those blocks are not just like anything can happen there. So T of V2, that gives you the second column of the matrix, right? T of V2 is V1 plus 3V2. Okay? But I can rewrite this like this. If you move this to the other side, so subtract 3v from both sides, the left side can be written as t minus 3 identity of v2 equals v1. And what I'm going to do is to apply another t minus 3 identity on top of both sides. Why would I do this? Because v1 was an eigenvector corresponding to the eigenvalue 3. So T of v1 equals 3v1. So by applying t minus 3 identity again on top of both sides, I get 0. Okay. This doesn't mean that v2 is an eigenvector of t, but it means it is an eigenvector of t minus 3 identity squared, if you want. But no, it is, in fact, what will be called a generalized eigenvector for t. Okay, well, so let's just make sure that we understand that all of them satisfy some kind of property like this. So we have V1, V2, V3, V4. Let's look at V5. Here V5. V5 is where is this one here is V5, right? Is going to be V4 plus 2V5. So T minus 2 identity, if you move this to the other side, T minus 2 identity of V5 equals V4. And then I apply it one more time. T of V4 equals to V4. So I get 0 again by 2 applications, right? As the one above. But that doesn't have to be the rule, as V6 will show. Where was V6? V6 is this one here, right? T of V6 is V5 plus 2 V6. Again, move 2 V6 on the other side. Now, with V5, in order to get 0, if you look above, it's not enough to apply T minus 2 identity. I have to apply T minus 2 identity squared to both sides. So that will give me the cube on the left. And finally, 0 on the right. So, what happens in general? If beta would be a kind of a Jordan basis for an operator T, what does that mean? The matrix of T in that basis turns into those blocks. And T then is going to correspond to some lambda. It's going to be in the block of some lambda. Lambda is the thing on the diagonal of that block. And T minus lambda identity raised to some power P of that V will be 0. So, yeah, for some P integer greater than or equal than 1. I will stop here for today and we'll continue Monday with this.